We had the software part 1 in the last episode. As promised, we go ahead with part 2 of the Arduino code for our DIY RF measurement device. In addition, we will see the setup for a 24 hours recording. In part 1, which was episode number 21, we covered the definitions, the settings, and the main program loop of our Arduino code. The code for the control elements and for some control keys we found already in the main program loop. In the part 2, we need to talk about a number of voids where we realized important functions. Besides the code, on our agenda today, there will be some more interesting content. After completing the Arduino code, we will demonstrate the configuration of the terminal program CoolTerm for the recording of a 24 hours measurement. Out of curiosity, we want to measure the incoming field strength from the surrounding radio services during a whole day in our house. Another interesting option for our device is the Arduino Serial Plotter. It is giving us a graphical view where we can see live the dynamics of the data. In the previous episode, we talked through the definitions, the setup, and the main program loop. Next, we need to cover the voids, which are the functions and the subroutines of our software. The first void creates the help menu. This is pretty obvious looking at the code here. There is nothing special about this one. However, I realized that the help text takes a lot of RAM memory. This is why I recall it from the flash memory, which is indicated by the capital F here. The next void is processing the data for the NeoPixel display. We get the values from the analog inputs, which we need to transform to the suitable numbers range to control the NeoPixel display. We need to do this for the inputs A1, A2 and A3. Then the NeoPixel display is activated. We need to consider the brightness value here, because it is adjustable, as you know. Next, we define the 3 colors for the 3 voltages. And finally, the show command activates the NeoPixel LEDs. The next void is processing the measured RSSI values for the NeoPixel display. It is similar to the previous void, however, we need to compute the current value and the adjustable P-cold value, which is displayed. The next void prints the units of measure for our values. And then we have the void printing the current parameter settings. Here I also recall the static string values from the flash memory in order to save RAM space. The next 2 voids are parsing the commands that are coming through the serial interface. And eventually the last two voids are printing the output columns for the text format. Well, that's the code for our little device. It is already close to the memory limits of the Arduino Nano. So, in case you want to extend the code significantly further, you might want to use a more powerful Arduino board. As promised earlier, I want to show the settings for a 24 hours measurement using CoolTerm and the PC to record the data. We start CoolTerm. You can make your life easy if you store the settings like I did here. I can just load the settings instead of fiddling with the parameter settings to find the right ones again. We go to the full screen mode. Here's the settings that you need to make the interface working. You need to choose USB serial here. The speed is 38,400 baud. We need 8 data bits, no parity bits and 1 stop bit. The rest is minor settings which I didn't change. Then we can connect. Our device is automatically sending the help menu and goes then automatically into the telematic mode, where it spits out all the available data separated by commas. We stop this using the key S. Next, we call the help menu by pushing the H key. We want to adjust the measurement interval Tn to 10 seconds. The help menu tells us that we can adjust Tn between 25 and an arbitrary integer number in milliseconds. Of course, 10 seconds is 10,000 milliseconds. The value for the number NO needs to be between 1 and an arbitrary integer number. And if we choose the number of measurements to be 8640, then we can cover exactly 24 hours with our measurements. In order to change these parameters, we open the window to send a string. We type in the commands with the new values. And after pushing send, we get immediately the feedback from the device about the new current settings. Then we can delete the window content. As we want to store our data in a text file, we need to start the capturing here. The program is suggesting a file name, which I accept. Then we push Start. Now we can request the measured data in text format by pushing the R key. And off we go. Again, we get the current parameter settings followed by the measured data. In fact, as intended, we get values after every 10 seconds. It is recording the RSSI measurements and the duty cycle, as well as the voltages on the analog inputs, where I connected a little solar panel. This is only for test. The voltage on A2 is basically telling us whether the light in the room is on or off. After 8640 measurements corresponding to 24 hours, our device will stop automatically. We don't want to wait for 24 hours in our demonstration here. I stop it manually with the S key so that I can explain the next steps. We can stop the file capturing now. And then we can disconnect and close CoolTerm. Let's see what we have recorded in the text file. Okay, that looks suitable to import to Excel. I will put the data and the Excel evaluation to the download section. Maybe you find that interesting. Here is just the summary of the Excel evaluation. I started the measurement at 3 p.m. and as said, we recorded measurements over 24 hours. With the antenna that I used, we see signals in the range of about 1 GHz to 5 GHz. We measure the physical field strength bigger than -65 dBm of all surfaces together in the air that we can detect. Of course, we cannot see any content of the signals. Obviously, the radio channels are busy during the day, while they almost disappear during the night. This is no surprise, because I switch off all my smartphones and Wi-Fi devices during the night. Even my router automatically switches off the Wi-Fi at 10 p.m. and it wakes up only at 6 a.m. I never did a measurement of this kind before. If I would integrate the field strength over time, it would give me my daily radio wave exposition. The graphic tells me immediately that the radio wave exposition in this frequency range in my flat is mainly made by my own devices. It seems that every other signal that comes from outside is at least 20 dB lower, which equals a difference of 2 orders of magnitude. Interesting, but not surprising, isn't it? The analog voltage from the little solar panel indicates that some sunlight came through the window in the morning, and in the afternoon the light was on. In case you don't want to record the measurements in a file, you can also use the Arduino IDE to monitor your measurements. Let me demonstrate this real quick. You can open the serial monitor in the Arduino IDE, and with that you can observe the incoming values, and you can also control the device by sending strings using the upper line. The other option is to open the serial plotter, which I find really cool, because you get a graphical representation of your values. You can also send control strings via the line on the bottom. In our case here, the measurement interval is a bit too slow for this. We can change the measurement interval to 25 milliseconds and we can see better the dynamics of the signal. Using the option O, we get RSSI, current, mean and peak value. We can also switch to the option A, which shows us the voltage at the inputs A0 to A3. The graph automatically adjusts the range after a while. The summary. We built a cheap measurement device for radio frequency power measurements. In addition, it can measure 3 analog voltages and it is able to send all the data to a PC for recording. The voltage measurement is not really accurate, however, for tinkering it is sufficient in most cases. Occasionally, we will see it in action in my projects. You can think of many other applications, like checking your microwave oven or in the field of amateur radio. Hope you got some insights and maybe you got some ideas that you can use for your own projects. Now there is one thing left to mention, the antennas. I'm especially in favor of magnetic antennas because they can make the device a bit more frequency selective to the bands of our interest. In some other episodes I will explain how to build antennas. In my case, the given concept works pretty well. That's why I have in mind to pimp my older RSSI gauge with the new concept. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.